Section 1.5, Measurement Uncertainty, Accuracy, and Precision. Here, we are looking at the difference between exact numbers and inexact numbers. Exact numbers are numbers that come from definitions. So for example, 1 liter equals exactly 1,000 milliliters, or 1 foot equals exactly 12 inches. These are exact numbers. They are by definition, or they are conversions between numbers. Exact numbers are also numbers that are derived from counting. So for example, if I have 32 students in the class, I can just count up how many students are in the class. Now, inexact numbers are values that come from measurements. We will assume that values derived from calculations are not exact unless otherwise indicated. So an inexact number is a value that comes from a measurement. I need to use a tool. So for example, how long a desk is. I can't just count how long a desk is. I need to use some sort of tool or instrument to determine how long the desk is. But now my measurement depends upon how good that tool is, right? If I buy a really expensive, well-made ruler from a company versus if I just buy a cheap one from the dollar store, the measurement I get from the really expensive ruler is probably a much more precise measurement than it is from the cheap ruler. So inexact numbers are values that come from measurements. They are inexact because they depend upon the precision of the tool or the instrument that is being used to measure them. Now, when we go to make measurements, especially in lab, you always estimate between the markings to 1 digit beyond what you are certain of. So for example, if I'm looking at a ruler here, and I'm using this ruler to measure this green bar. So you notice that this green bar, it falls pretty much exactly in between two lines. So right here, we've got the 23 line, 23.1, 0.2, 0.3, 0.4, 0.5, 0.6. So this line right here is 23.6. This line is 23.7. This green bar falls directly in between 23.6 and 23.7. So I am certain that this green bar is at least 23.6 centimeters long. But that final reading there, I don't know exactly where it is, right? It falls somewhere in between 23.6 and 23.7. So you want to estimate between those markings to 1 digit beyond what you are certain of. So this would be read as 23.65 centimeters. The 23.6 is certain, and then that 0.05 at the end is estimated. If we were doing this with a graduated cylinder, same idea. Estimate between the markings and go 1 digit beyond what you are certain of. Now it's important with graduated cylinders that you read at the bottom of the meniscus. So a meniscus is this sort of elliptical-like shape. This happens because of surface tension, where the liquid will kind of grab onto the side of the walls of the container. So you want to read, make your mark here, make your reading at the bottom of the meniscus. So in this situation, this graduated cylinder is marked every milliliter. So I am certain that the water in this graduated cylinder, it occupies at least 21 milliliters, but the final digit there I'm not certain of. It's somewhere between 21 and 22, so this could be read as 21.6 milliliters. The 21 is certain, and the 0.6 is estimated. If we're doing this with a more precise instrument, so let's say I have a graduated cylinder that's marked every 0.1 milliliters. So here the meniscus falls right on the line. So here we are certain that this water has a volume of at least 8.00 milliliters, and then you would estimate your final digit. But because this water falls directly on the line, this would actually be read as 8.00. If you said just 8.0, that would be wrong, because you need to estimate 1 digit beyond what you are certain of. So since this is marked every 0.1, we are certain of those first 2 digits, and then this here is an estimated digit. Since to my eye, it looks like this falls, the bottom of the meniscus falls right on the line. So 8.00 milliliters would be the correct reading here. Now when you go to use a digital scale in lab, this is very easy. Just report all digits directly from the digital scale or from the balance, unless otherwise instructed. So the balances we'll be using in lab, they go to 4 decimal places. So just write down what you see on the screen. Now let's briefly talk about the difference between mass and weight. So they are slightly different from one another. Mass measures the amount of matter in an object. It does not depend on gravity, whereas weight is a measure of gravitational attraction between the object and, for our situation, the Earth. So weight essentially is a force. It depends upon the mass, but it also depends upon the gravitational attraction or the acceleration. So if you were on the Earth, if you were between the Earth and the Moon, or if you were on the Moon, let's say you had a mass of 65 kilograms, your mass doesn't change because mass measures the amount of matter. But on Earth, you would have a weight of 637 newtons. Between the Earth and the Moon, you would functionally have no weight. You would be weightless because there is no gravitational attraction in space. If you were on the Moon, you would have a weight of about 106 newtons, since the Moon has approximately 1/6 the gravity that Earth does. All right, now let's get into everyone's favorite subject, significant figures. So significant figures are very important. You need to understand significant figure rules. You need to understand what is a significant figure. And here later in this section, we're going to talk about sig figs as they relate to operations. So to express the precision of measurements and calculations, we use significant figures. So significant figures are very important when we are working with inexact numbers, when we are working with measurements, because as I illustrated in the example earlier, how precise that measurement is depends upon the precision of the tool, of the instrument that you are using. The more precise the instrument is, the more precise your measurement is, and thus the more significant figures that it has. Now, let's look at this number right here, 0.004004500. These three zeros out front, we're going to talk about them in a minute, these are not significant. So this 0 is really just for cosmetic purposes. These two zeros right here, they're used only to locate the decimal place. They are essentially value placeholders. They are not significant. Now the 4, and the 5, these are significant because all non-zero integers are significant. These two right here, they are significant because they are between non-zero integers. So these two zeros are significant, and these two right here are also significant. So let's break this into categories. The 5 rules for significant figures. The first one, the easiest, all non-zero digits are significant no matter what. So 112.1, this number has 4 non-zero digits. This number has 4 sig figs. Second, these are what I like to call captive zeros. Captive zeros, they are zeros between non-zero digits, and they are always significant. So 50.08, the 5 and the 8 are significant because they are non-zero digits. These two zeros are captive. They are between the 5 and the 8, so they are significant. So this number has 4 sig figs. Next, rule number 3, I like to call these leading zeros. Zeros to the left of non-zero digits are not significant. So 0.0023. These 3 zeros, they come before the non-zero digits. They are leading zeros. They are simply value placeholders. They are not significant. So this number has 2 sig figs, the 2 and the 3. Finally, rules 4 and 5 are what I like to call trailing zeros. Trailing zeros are sometimes significant, sometimes they are not. Trailing zeros that are to the right of non-zero digits in numbers that include decimal points are significant. So this number right here, the 1 and the 2 are significant. These two zeros are trailing zeros. They appear to the right of non-zero digits, and they appear in a number that has a decimal point, so they are significant. So this number has 4 sig figs. Now, if the number does not have a decimal place, we're going to treat those zeros as being non-significant. So 100, the 1 is significant. These two zeros, they are trailing zeros, and the number does not have a decimal place. So this has 1 sig fig. Now, if I wrote in a decimal place right here, now my number would have 3 sig figs because these zeros are now in a number that does have a decimal place. So now all 3 digits would be significant. So if the decimal place is present, trailing zeros are significant. If there is not a decimal place present, trailing zeros are not significant. All right, let's try a knowledge check. How many significant figures are in the number 32.800? All right, the correct answer here is 5. All 5 are significant. 3, 2, 8, and the trailing zeros because there's a decimal place. All right, one more question. How many significant figures are in the number 67,400? Correct answer here is B, 3. The 6 and the 7 and the 4 are significant. The 2 zeros are not significant because there is no decimal place. So those trailing zeros are not significant. All right, last thing here on what is significant and what is not significant, scientific notation. So when looking at significant figures with scientific notation, if a number is expressed in scientific notation, all digits in the coefficient are significant. The power of 10 represents zeros that are just placeholders, which gives us a sense of the size of the number. So here, these 4 digits, they are significant. All 4 are significant. So all of the numbers in the coefficient are significant. Then this just represents your placeholder values. So this number would have 4 sig figs. How many significant figures are in the number 4.300 times 10 to the negative third? All right, correct answer is C, 4. All 4 of these are significant because they are a coefficient in a number represented with scientific notation. Now briefly, let's talk about rounding. So you may, in some of your problems, need to do some rounding to express the answer with the proper number of sig figs. Now the rounding, we're using the same basic idea. If the digit to the right of the final digit you want to retain is less than 5, round down. If that digit is 5 or greater, round up. So if I had the number 7.94 and I wanted to round to 2 sig figs, okay, well I'm keeping the 7.9 and then my next digit is a 4, so I'm going to round down to 7.9. Now if I had the number 7.95 and I wanted to round to 2 sig figs, well I'm keeping the first two, 7.9. If I look at the next digit to the right, this is a 5, I need to round up. So now my number would be expressed as 8.0. Next, let's talk about rounding using sig figs with operations. So addition and subtraction and multiplication and division have slightly different rules. So with addition and subtraction, first you want to determine whether each value is exact and ignore exact values. We're going to treat exact values essentially like they have infinite sig figs. Next, you want to determine the number of decimal positions for each value that is not exact. Finally, round your answer to the same number of decimal positions as the inexact value with the fewest decimal places. So let's look at an example. What is the sum of 9.572 and 82.76? So 9.572 plus 82.76, my unrounded answer is 92.332. So let's look at both of my component numbers here. 9.572 has 3 digits after the decimal, or it has 3 decimal places. 82.76 has 2 digits after the decimal. So my answer needs to have the same number of decimal places as that component number that had the fewest number of decimal places. So essentially that means my answer should have 2 digits after the decimal. So I need to round here. So I'm going to keep the 92.33. Look to my next number. It's less than 5, so I round down, and my answer is 92.33. All right, let's have you try an example. What is the sum of 10.52 and 8.955? All right, correct answer here is 19.48. So you needed to round here. This number has 2 decimal places, this number has 3, so your answer needs to have 2. So this gives 19.48. All right. Now let's look at multiplication and division. So the rule here is slightly different. Now the steps are generally the same. First, again, determine whether each value is exact, and you can ignore exact values. Next, determine the number of significant figures for each value that is not exact. And step 3, when you multiply and divide, round your answer off to the same number of significant figures as the value used with the fewest significant figures. So addition and subtraction is based upon number of decimal places. Multiplication and division is based upon total number of significant figures. So for example, what is the product of 4.38 times 695.1? So 4.38 times 695.1, my unrounded value is 3044.538. Now this number has 3 sig figs. This number has 4 sig figs. This means my answer needs to have 3. So I'm going to keep the 3, the 0, and the 4. Look to my next digit. It's less than 5, so I round down, which makes my answer 3040, or 3.04 times 10 to the third. Either is acceptable, and either expresses my answer correctly to 3 sig figs. All right, let's have you try one. What is the result of dividing 607.90 by 9176.74? All right, correct answer here is C, because this number has 5 sig figs, this number has 6, so my answer should have 5 sig figs, 0.066244. All right, let's briefly talk about multi-step calculations. Now, when you go to do multi-step calculations, first I would recommend doing the full calculation first without rounding. So let's say I was doing 1.23 plus 2.5 divided by 2.75. So I would do my addition first and then divide by 6.75. This gives 0.550074. Now also, you want to go back through the calculation again and pay attention to proper sig figs. So if I do the addition up top first, I get 3.7 because this number right here has 3 decimal places. This number has 1, so my answer needs to have 1. Then do my division. And we're going to keep 2 sig figs on our answer because this has 2 sig figs, this has 3. So 0.55074. I'm going to keep just 2 sig figs, so I'm keeping the 5. Look at my next digit. It's less than 5, round down. This makes my answer 0.55. So pay attention to sig figs, especially if it is a multi-step calculation that involves different operations, because the addition-subtraction rule is slightly different than the multiplication-division rule. Let's look at a multi-step calculation lab example. So one of the first labs we're going to do, measurements and density of a solid, is you're going to attempt to figure out the density of a solid based upon Archimedes' principle. So I've got water in a graduated cylinder, and I've got this regularly shaped solid, and I want to determine what the volume of this solid is. So to do that, I'm going to take the solid, place it in the graduated cylinder, and then figure out the volume based upon how much water it displaces. So my initial volume is 13.5 milliliters. The final volume after adding the rebar is 22.4 milliliters. The rebar has a mass of 69.658 grams. So to find the density, I would do mass divided by volume. The mass is 69.658 grams. The final volume is 22.4. The initial is 13.5. So to find the mass of the rebar, take final minus initial. So 22.4 minus 13.5 gives 8.9 milliliters. Remember, your answer here would not be 8.90. This number has 1 decimal place. This number has 1, so my answer should only have 1. So now I take 69.658 grams divided by 8.9 milliliters, or 8.9 centimeters squared, since a milliliter and a centimeter squared are the same. Unrounded, this gives 7.8267 grams per centimeters cubed, but I need to round to 2 sig figs, since this number has 2 sig figs. So my final answer would be 7.8 grams per centimeters cubed. So this rebar has a density of 7.8 grams per centimeters cubed. All right, let's wrap up by talking about accuracy and precision. So accuracy is how close your value is to the true or accepted value, or the theoretical value. We will determine this in lab using percent error. Precision is how close your measurements are to one another. This is determined in lab with standard deviation. So let's pretend we were at the range and we were doing some target practice. So here, if all 3 shots hit directly in the bullseye, This is both accurate and precise. All three shots were very accurate. They were close to the center, or they were close to the true or accepted value. They are also all very close to one another, so this is very precise. Here, this would be an example of being precise but not accurate. We are pretty far off from the center, or we are pretty far off from the true value, so we are not accurate, but all three are very close to one another, so this is precise. Here, this would be an example of being both not accurate and not precise. Alright, so that concludes section 1.5. I'll see you in the next video for our final section 1.6, mathematical treatment of measurement results.